Hello, everyone. My name is Omar Jimenez. Um, with partnership with Harvard College, Claremont McKenna College, I will be presenting Learning to Drive for my final project. So, starting with the problem statement, I want to focus on training a reinforcement learning agent to navigate a racetrack using raw pixel observations. And this is done in the car racing environment provided by Gymnasium, which is an API standard for reinforcement learning. And the action space here is a continuous steering, so I could go right or left, gas, brake. My observation state is just raw pixels from the screen. Um, my starting state is, just being in the middle of the road, as you can see on the right. And my reward function here is a little tiny um, negative reward for every frame, giving it the incentive to try to go fast. And I get a good reward for every tile it explores. So this encourages exploration, staying on the track, and trying to complete it. And if I'm completely off of the track, I also get um, a super big negative reward and the episode ends. Um, Otherwise, the episode will end once we've completed the track. So I want to evaluate these algorithms by tracking the expected reward per episode. Uh, and as the agent is rewarded as it goes through the track, I want to then plot this average reward over dozens of episodes, as we will later see, to see how efficiently our agent has learned how to drive. So how'd I do it? So here's a little bit more about my setup, get a little more technical. Um, I utilized three wrappers to kind of try to manipulate my data as much as possible because I have a screen. They don't give me the data directly of what my car is doing. I got to figure that out. But a whole screen is a lot of data. So I convert um, my screen into a grayscale. I normalize it, try to blur it a little bit, and then I use a frame stack wrapper to keep some of the motion that I'm going to need. I also took the time to train a baseline agent. So this agent chooses actions at random. It just does random stuff, doesn't take into account the reward function, doesn't take into account where it's been, where it's at, where it's going. Uh, and I got us a score of three, unsurprisingly, because it's not doing much. It's just it's just having an outrage. Um, Also did some autoencoder training, and in our case, I only collected 500 frames due to the small scale of this project. Something a little bigger with more episodes would have required collecting thousands of frames. And this leads to our reconstruction loss being a lot lower, um, as you would expect that to be a little higher with more frames. But uh, as I collected so few to train my autoencoder, that explains the low loss on efforts to try to get results by the deadline. Um, so just to reiterate the reinforce algorithm that I will be using, this is a Monte Carlo policy gradient adapted for continuous control. Um, so just as a little recap for each episode, the algorithm collects the entire trajectory from its current state, then computes discounted returns, advantages to then update its policy and its baseline policy being how it's going to act in the future. So we have two agents running on this, but one of them is fed data using a convolutional neural network, an end-to-end CNN, and uses CNN feature extractions that are more accessible and more flexible for me but also, as we will see later, a lot slower. It takes a lot longer to train as it's getting more, it's being stimulated a little more. But Agent B uses that autoencoder that we previously trained. And as I mentioned before, it sees a little blurry. But the thought process here was that it would be able to be trained faster and thus run more episodes and hopefully have a more efficient way of training. Um, but as we could see based on our results, we were able to run and train our agents with 30 episodes each, which surprisingly at the time was surprisingly to me took over 3 hours to run just for 30 episodes. This all happens in real time, so we have to wait for its agent to finish running as we move on to the next one. But here you could see some great preliminary results based on what given our constraints. Specifically, Agent A saw great growth that is further demonstrated by the following graph. Here you could see that Agent A has grown in its score, in its average score, a lot faster. As we mentioned before, it was receiving more features, more data. So this is what you could expect. And Agent B, because it's being stimulated a little more, um, or because it needs more time to 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 learn um, patterns because it's not getting as much. It's getting the auto-encoded information. So you would expect that it would take more episodes to actually show some growth, which is what is shown here with our 20 episode experiment for each one. But this shows and proves that at least Agent A was learning how to drive. It got a better score, as we saw in the last slide. It got almost a score of 18, which is definitely a lot better than the random agent score of 3. So showing those type of results with the constraints that we had was very encouraging. And given an agent that is learning a little more, you can expect to see something like this, where it's avoiding the grassy paths and it's doing its best to explore the racetrack as fast as it can, like any other driver would. So I learned a lot from this. I learned that training takes forever. It's all in real time. It could take hundreds of episodes to truly learn something. I learned that professional RL engineers use a method called parallelization, which was a bit out of my scope for the scale of the project. But they're essentially able to run episodes in parallel and then update their policy together, which increases which decreases the time it takes to train pretty drastically. As we saw earlier, 30 episodes took hours to run. So doing hundreds of episodes would have taken days. And for my timeline, where I had about a week to do the project, just wasn't feasible. But I'm very happy with the results that I got, given I was able to show my agent learned at least a little bit how to drive. So I'm pretty happy with that. Ending off on a little bit of a high note. I'd like to thank you and thank my professor Teal and the rest of my peers for an amazing semester.